Okay, let me recap our course in the last week. I want to share my screen. Okay. Wait a minute. Can you see my share screen? Okay, this is second week. We have an event of international collaboration with me, Dimas Setiawan from Universitas PGRI Madiun, and we have a lesson outcome, computer definition, overview, and history of computer, basic component of the phone human architecture, electronic data and instruction, system units, and input-output device. In the last week, we have talked about computer definition, overview of history of computer, and component of the phone human architecture. And in this course, we will talk about electronic data, system unit, input or output devices. But let me recap our course in the last week about computer definition. Computer definition is an electronic device. It operates under the control of instruction, which we call a program. And it's stored in its own memory, which can accept and process the data according to specific rules. And computer can produce results and store the results for future use. This is about computer definition. And last week we have talked about overview and history of computers. History of computers divided into two categories: before 1940 and after 1940. Okay, before 1914, in this era we find technology in the mechanical era, such as the abacus, the tools used to calculate in the Roman era. And after that, we know about Blaise Pascal with Pascali. We know about Gottfried Wilhelm von Leibniz and Carlos Xavier Thomas de Colmar, who find the first calculator. And after that, after 1940, we know about computer are divided into fifth generation. In first generation, which is popular with vacuum tube technology, makes all electronic device have a big size like an ENIAC, ECFAT, etc. And the second generation, which is popular with the invention of transistor technology, which was helpful in the development of computers and changing the vacuum tube tech. And the third generation, we know, the popular with Jack Kilby, the inventor of the IC-based touch or integrated circuit touch, which one with these technologies makes all electronic devices have a smaller size, less heat, faster, and more reliable in comparison to previous two generations, but still costly. And the fourth generation, the goal of developing computers make smaller circuits and component sizes. And in this generation, we can look at large-scale integration of LSI and VLSI. With VLSI permitted the thousands of transistors to be integrated into one single chip. And the fifth generation, We know we talk about how computer develop to be faster, be intelligent, and cool, such as the robot era, artificial intelligence era, and ULSI technology, which one integrating or embedding millions of transistors on a single silicon semiconductor microchip. This is the recap of our course last week. And last, we talk about the von Neumann architecture. This is John von Neumann. We know, but von Neumann have a 5 element or component of the architecture. There is a central processing unit or CPU. It contains the control unit or CU, and arithmetic logic unit or ALU, and interface unit. And we know about a memory. This is a short-term storage for CPU calculations, holds both instruction and data of computer program. And the third component is input device. You know about keyboard, mouse, scanner, pads. And the fourth is output devices like a monitor, printer, fax machine, and the storage like as a hard drive, optical media, diskettes, magnetic tape. And in the von Neumann, the all of architecture is linked by bus, a bundle of wires that carry signals and power between different components. This is about von Neumann architecture. Okay, and lesson today, we will learn about 3 subtopics. We will talk about electronic data and instruction. And second, we talk about system unit, include system board, microprocessor, RAM, and ROM. And the third, we will talk about input-output devices. And I want to ask you about a question. What do you know about data? Can you give your opinion, class?
And information.
Information, okay. Any answer? Data is information, okay. Any answer? Have you another answer? Or all in this class agree about data is information? Hello, class.
We agree with data is information.
Okay, every people agree data is information. Actually, data and information is different things. Data is a single fact, atau dalam bahasa itu adalah fakta, satu fakta. And about information is informasi itu in bahasa adalah hasil dari pengolahan data. The process of data, we can call it information. Are you understand, class?
Yes.
Yes, okay. But we have a interest topic about the data. Actually, data can be analog or digital. Okay. And analog data is our continuous and take continuous values. You can look the screen. What is that picture?
Sound.
The wave of sound. Okay. Any answer? Any other answer? Or all classes agree this is a wave of sound? Hello?
Yes, sir.
Yes. Okay. This is a visualization of wave of sound. Okay. And we know about the analog data example, the sounds made by a human voice take on continuous values. When someone speaks, an analog wave is created in the air. And this can be captured by a microphone and converted to an analog signal or sampled and converted to a digital signal. This is about analog data. So this is everything about we talk, everything about we look. This is about the analog data. Computer can be capture everything moment of your voice, of your everything. What do you speaks? And this is to be encoding to some binary or digital. And we know data can be analog and can be digital data. Digital data is have discrete states and takes discrete values. And the example, data are stored in computer memory in the form of zeros and first or ones. They can be converted to a digital signal or modulated into an analog signal for transmission across a medium. So we know a computer is a machine, and we also know computer have definition to calculate, and computer have on or off states, and computer have 1 or 0 states, and it's called binary system. And this is, do you know the metric, which has an actor Keanu Reeves?
Yes, yes.
Have you ever seen before?
Yes.
Yes. What do you think about this film? Can you explain me? You can explain with English or explain with bahasa. What is comfortable for you? You can explain it about the metric. Silakan teman-teman. Kira-kira pernah lihat film metrik kan? Bisa menceritakan nggak film metrik itu apa?
Hidup dalam komputer.
Hidup dalam
Dunia tipu.
dunia tipu ya. This is a virtual world. Like this. Yes. And in the metric, we can look the scene of this. Have you ever seen before in the metric movies? About 1 and 0 and the effect of screensaver on the metric movies. Actually, computer, we have many questions about the computer. How computer calculated? How 1 and 0 can be calculated and be some produced that we see on the monitor screen. Actually, the metric film is movies which one visualization of a virtual world. And that is how the film can explain computers can calculate number 1 and 0 into image, videos, text, movies, etc. Actually, the computer can be produced image, can be produced videos, text, movies, etc. Computer have a function to calculate. What calculate can be do of the computer. Computer calculate 1 and 0 because computer just a machine and machine have two states. There is on or off states. And the question is, how computer calculated, how 1 and 0 can be calculated and be some product that we see on the monitor screen. In bahasa, bagaimana komputer itu bisa menghitung angka 1 dan 0 untuk menjadi video, foto, teks, bahkan film yang teman-teman suka. The answer is character encoding. Okay. Do you know about character encoding, everyone?
Ya,
Tidak.
No.
No. Okay, we will talk about character encoding. This is a interest topic. Okay, if we talk about character encoding, okay, wait a minute. Character encoding standards is a unique sequence of the binary representation of a particular letter, number, or special character, and it is used to facilitate communication among computers by using a common language code. Okay, this is about a character encoding in definition, and we will simulate about of binary conversion. Okay, I will close my presentation and look how the computer can calculate everything in the 1 and 0, text, and etc. Okay. Okay, this is repeatables.com. This is if you learn about character encoding, you will find about ASCII, ISII, or American Standard, and hexadecimal, binary decimal base 64 converter. Actually, if I text my name, Dimas, we have 5 letters: D, E, M, A, and S. But the computer read the text, not the letter, but the binary. The computer look what I input is 10 111 10 000 100 is for letter of D. Okay. And if I add the letter of I, we will look the binary is 0 1 1 1 0 1 1 1. This is about a binary to text. Are you understand, guys?
Yes.
Yes. This is how the computer calculate everything. So what we seeing in the monitor, like a color, like a text and everything, picture, computer can produce, can atau dalam bahasa tidak bisa melihat itu semua. Tetapi komputer hanya bisa melihat angka 1 dan 0. The state of machine 1 and 0, on or off, just like that. And basically, the programming language we learn, like Java, HTML, CSS, C#, C, and etc. It's just produce development of binary language. We can use binary to give some instruction or code to produce something. It makes a long time to process and make us so tired. So can you imagine if computer calculating everyone about 1 and 0, you can imagine the smartphone of your phone. This is not have a keyboard, atau dalam bahasa saya ingin menjelaskan dengan mudah. Bayangkan kalau di komputer teman-teman atau handphone teman-teman itu tidak ada huruf A sampai Z gitu ya. Hanya ada huruf 0 dan 1. Can you imagine that? What happened? Can you explain that? Adakah di sini yang bisa menjelaskan seandainya kita punya keyboard itu bukan A sampai Z, tetapi hanya ada angka 1 dan 0, or binary keyboard. What happened?
Susah, Tai.
Hilangkan
This
dulu.
Yes, this is make us a long time to process and make us so tired. For example, if you have tags, you must text on your computer and say hello to your girlfriend or boyfriend. Hi. Okay, we can simulation. Hi. Apa kabar? You must typing about the binary language 10, 11, 00, and after that. This is a long time process. Actually, the computer convert everything, the binary to hexadecimal and decimal and 4 under the length, the bits. This is about RSTI double-2 text to hex conversion table. You can look of the character. Okay, I have a sample. This is about letter A. So letter A in hexadecimal is have a code 41, but in binary they have a standard 1 0 1 0 0 0 0 0 1. This is like a dictionary about the how computer can calculate everything. I have some videos to make your easy to understand about everything about how binary work, etc. But after I explain about this course, okay. We will back in our presentation. Okay, wait a minute. Okay, this is the simulation of binary conversion. This is interest topic, and after that, we will let's see some videos about image, pixel, and RGB. And second videos, we will look about manufacturing of microprocessor. The third videos, we will look about masking of the architecture technology, how a CPU is made. Okay. The first video is talk about wait a minute.
Good.
I created Instagram with my co-founder.
Okay, I found this video is so unique. This is tell about how the founder of Instagram explain about the bit and pixel and RGB. We know every people, me, you, and your family, and everything in this world like a picture, like some art about visualization. So this is will explain about the how picture can make in your screen monitor and how the binary work together in this picture.
Good.
I created
this video, can you look? Okay, minute. I will share screen again. Okay.
Good.
I created Instagram with my co-founder, Mike. Initially, we saw the mobile phone as an opportunity to create something new because for the first time, people were carrying around a computer in their pocket. And we decided that sharing imagery was probably the biggest opportunity for the next 5 years and one that we held close to our hearts, something we wanted to spend our time on. It's great to say you have an app or an idea that does X, Y, or Z, but unless that solves a real problem for people, they're not going to use it. And the question is, what problem are you solving?
When people first faced the problem of how to show a picture on a screen, they had to come up with a way to break the image down into data. In 1957, an early computer engineer named Russell Kirsch took a picture of his infant son and scanned it. It was the first digital image, a grainy black and white baby picture. And that's how the pixel was born.
Pixels are an interesting concept because you can't see them very easily. But actually, if you get a magnifying glass and you go up to a screen, you actually can see that your screen is made up of tiny dots of little light. What's more interesting is that those tiny dots of little light are actually multiple tiny dots of little light of different colors. There's red, green, and blue. Pixels together from far away create an image. And up front, they're just little lights that are on and off. And the combination of those create images and what you see on your screen every single day you use your computer. So you'll hear the term resolution a lot, both in computer science and manufacturers of devices will talk about it. Resolution is basically, it is the dimensions by which you can measure how many pixels are on a screen. So back in the day, when I was a high school student, it was 640 by 480. And today it's a lot bigger. And then there's the question not only of resolution, but also of density. So for instance, on modern smartphones, they fit the same number of little lights called pixels, but in a denser space, and it's what allows you to get sharper images. Now, how do you store those values of the pixels in a file? So what you do is you store red, green, and blue values in little triplets effectively, with different values that each make up a single pixel. So the values range from 0 to 255. 0 would be very dark, 255 would be very bright. And triplets of these values together compose a single pixel.
An image file, whether it's a JPEG, GIF, PNG, etc., contains millions of these RGB triplets. So how does the computer store all that data? All computing and digital data are represented by bits. A bit has two states, it's on or it's off. But instead of on or off, computers use ones and zeros, binary. So an image file is actually just a bunch of ones and zeros. But why do RGB values go from 0 to 255? Turns out that each color channel, RGB, is represented by 8 bits, which together are called a byte. If you know the binary number system, you know that the maximum number 8 bits can represent is 255, which is equal to 8 ones in a row. And the lowest is 0, or 8 zeros in a row. Therefore, 0 to 255 gives us 256 different intensities per color channel. We could represent a pixel of the color turquoise, for example, in our traditional decimal-based number system as 64 for a little red, 224 for a lot of green, and 208 for some blue. But a computer would have stored it as 01 00 0000 111 00000 1101 0000. We use 24 binary digits to represent this one pixel. So rather than binary, digital artists often use the hexadecimal number system to represent colors. So we can represent the same color turquoise using only 6 hexadecimal digits, so 40, E0, D0, which is a lot shorter.
Let's say you want to modify the colors of the image. How do you do that? Basically, there are ways of mapping functions where you take the input value of the pixel, so you take an input of a red, green, and a blue value, which represents that color, remember, and then you map it using a function to a new red, green, and blue value. Let's say you wanted to make an image darker, right? One way of doing that is by taking the red, green, and blue values that come in, and let's just say subtracting a fixed constant from each of them. So subtract 50, right? And obviously you can't go below 0, but you just subtract 50 from each of them. And that's the output. So the input is RGB, and the output is R minus 50, G minus 50, and B minus 50. What you'll see is you take in an image with a certain brightness, and you get out an image with a much darker brightness. What a lot of people don't realize about Instagram is that initially people thought what it was a way of filtering your images, making your images look cool in some way or retro. And what it grew into was actually much more important, was a way of people connecting. So it's not just about seeing photos of your friends and your family, but actually being able to discover things happening all around the world. Whether that's a riot overseas, a social movement, you're able to basically consume that information in a visual way. And that allowed us to grow very quickly and be a universal platform.
Okay. This is one videos about image, pixels, and RGB. We know RGB have a standard and 0 until 255, just like that. This is how we can look about this video, how this explain everything about image, pixels, and RGB. And the next, we will talk about second topic, okay, about system unit. If we talk about system units, we have several types like a desktop, laptops, tablets, smartphone, and wearables devices. But all devices on many types have similarities such as system board. So the system board, we can call it main board or motherboard. And this board have a function to control all data communication for the entire computer systems. And system board have many sockets, many chips, and have some additional component to improve capabilities of computer. And the system units of all devices have a microprocessors. We know a desktop, laptop, tablet, smartphone, and wearable devices have a microprocessor. We can call it CPU or central processing unit, and we can call it brains of the computer. Microprocessor have two components. There is a fundamental architecture. There is control units which have a function to tell computer how to carry out a program's instruction, and LU, which have function to perform arithmetic and logical operation. And the last, we know about the system units have a memory. Everything about electronic devices like a desktop, laptop, tablets, smartphones, and wearable devices have a memory. What's the memory function? We know the function is to save some instruction program, some files, and save anything data what we want. But memory chips have three types, like a RAM can be called volatile or temporary, or virtual memory, because the RAM is loses its contents when power is turned off. Different with room and flash memory, they can be called non-volatile memory because they does not lose contents when power is removed. This is about memory. And the third topics, we will talk about input or output devices. This is an easy topic, and you know, data that gets into the computer is called input. and information comes out in the form computer is called output. Input devices, as we know, input devices are hardware components that allow users to enter data and instruction into a computer or mobile devices. The example of the input devices is like joystick and the microphone, mouse, the camera, the scanner, just like that. And the last, we will talk about output devices. In output devices, we have a definition. Are any hardware component that convey information from a computer or mobile device to one or more people. We know the example of output devices is like a monitor, sound, and headphone, and the last is a printer. This is about topics today we will talk, but before we end our course, we will look some videos about how the microprocessor works. We know the microprocessor can call it brains of the computer, and we know the technology can be cool thing and good thing. It's because they have a microprocessor. So we will look about the manufacturing the microprocessor. I have a video. This is microchips. How a CPU is made. So in this video, we will look closerly about how the CPU is made, how the brain of the computers is made.
You are about to experience a fascinating journey through the clean rooms of the semiconductor industry. See integrated circuits in the making at one of GlobalFoundries chip factories. Let our experts walk you through the nanocosmos of the atom. A world that normally remains hidden from our eyes. In the beginning is the circuit diagram. At design centers around the globe, experts collaborate to design circuit diagrams, sophisticated integrated circuits like microprocessors, high graphic processors, and wireless communications ICs. The next step is manufacturing. The disk substrates for the microchips are made from quartz sand and are called silicon wafers. To make these wafers, a huge monocrystal is drawn from purified silicon melt. The result is a perfect silicon lattice into which the transistors will later be fitted. However, impurities pose a threat to these flawless silicon crystals. Our GlobalFoundries manufacturers must therefore take extensive precautions every time they enter our dust-free clean rooms. The result? Our wafers are fabricated in an environment that is more than 100,000 times cleaner than an operating theater. Completely free of dust, the silicon discs arrive at the clean room. Here, 25 wafers are packed into each hermetically sealed container and sent off on a journey that will take them through hundreds of manufacturing steps. Photolithographic techniques transfer the circuit structures to the wafers, rather like slide projection. The key to this whole process is a solid mastery of light. The silicon disc is spin-coated with a photosensitive resist. UV light transfers the circuit structures depicted on a mask to the wafer. The exposed parts of the resist are soluble and are removed by a developer. The transferred structures can now be used as a template. The unprotected parts of the water surface are etched away. The structures of billions of small current switches are generated on each wafer, tiny transistors. From the photolithographic stage, wafers move on to the ion implantation, where the electrical properties of the transistors will be specified. Here, the engineers make good use of one of silicon's most important properties. Silicon is a semiconductor, which means that its conductivity can change via a high precision emplacement of so-called dopant atoms. First, dopant atoms are injected into the silicon structures. These atoms then distribute randomly in the silicon lattice. At high temperatures, the doping atoms become flexible and take on a fixed position in the atomic structure. The complexity of manufacturing tiny transistors requires a clean room as big as 2 soccer pitches. While our people monitor the complex processes, automated manufacturing itself always takes place within hermetically sealed production lines. Copper dominates the next process step. The finest interconnect wires link up billions of separate transistors to form integrated circuits. Before that can happen, however, cleaning is essential for wafers, as particles lurk at every stage in the manufacturing process. Before the copper is poured into the trenches for the interconnects, a barrier layer is applied. It helps to avoid short circuits and guarantees reliability. The trenches are then filled with copper. Finally, the excess copper is ground down to the edges of the trenches. This insulates each interconnect from the others. A microchip made of copper wiring established GlobalFoundries as the first company in the world to adopt copper in volume production. A foundation for the state-of-the-art multi-core processors that GlobalFoundries is introducing today in all product areas. To keep us on the leading edge of the world's chip makers, electron microscopes constantly monitor every step in the manufacturing process, down to the atomic structures of each individual transistor. In 2 months, the wafer is ready. Huge integrated circuits consisting of conductors with a length of multiple kilometers link up 100 billion transistors on numerous levels. And that in a space no larger than a fingernail. GlobalFoundries, the first truly global semiconductor foundry, located in the USA and Germany, Fab 1 in Dresden and the future Fab 2 in Malta, New York. Together they'll be 2 of the most advanced chip factories on Earth and a testing ground for the very latest microelectronic innovations from around the globe. The last production step in microprocessor manufacturing is the packaging of the chips. In preparation for this step, tin silver pellets are applied on the wafer. They will link the chip to the frame. Via the finest saw blades, the chips are cut off the wafer. The flip chip method is used to bond the chip to the frame, which is sealed with a cover.
Okay, that is so cool. We look about the manufacturing process of the GPUs is made. They built from some element like sand, water, light, and fire, and etc. This is a brain of the computer. And I have a second videos about how our microchip makes.
This microchip can take up to 26 weeks to make. In its as many as 100 layers, billions of transistors are packed into an area about the size of a fingernail. They're the brains behind almost everything we use in our increasingly electronic world. Here's how these complex, tiny devices are made. The process begins with silicon-rich sand. Why silicon? Silicon is a semiconductor. It's the sweet spot between an insulator and a pure conductor. That means its properties such as its conductivity can be altered by adding impurities or doping to meet the needs of different electronic devices. This also allows us to control the electrical signals that pass through. Silicon is also abundant. It's one of the 10 most common elements found on Earth. But much of the silicon found in the wild is chemically bound to oxygen, so the 2 elements must be separated. The sand is combined with carbon and melted in crucibles to produce carbon monoxide and 99% pure silicon. After further processing, ultra-pure silicon is produced. Next, a seed crystal is placed in contact with molten silicon. As the seed crystal is slowly pulled away, silicon atoms are deposited on the bottom surface. The result is a large cylindrical boule, or a single crystal ingot of pure silicon. The boule is then thinly sliced into wafers. Silicon wafers typically have diameters of 1 to 12 inches, with the most state-of-the-art facilities being able to produce wafers up to 18 inches in diameter. Bigger wafers are, of course, able to yield more microchips. Once the silicon wafers are cut, the production process begins in full. Microchips are made in extremely sterile conditions, free from contaminants such as dust. If even just one particle of dust makes its way onto a silicon wafer, the entire batch is at risk of being ruined. This would derail a process that can take an average of 12 weeks. The first step of the production process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the surface of the wafer. Then the silicon wafer is prepared for lithography by coating it with photosensitive and light-resistant materials. The next step is very critical: exposure. The prepared silicon wafers enter a lithography machine and are exposed to UV light passed through a reticle containing the chip's blueprint. The areas exposed to light are hardened, while unexposed areas are then etched away by hot gases to leave a three-dimensional microchip. The electrical conductivity of different parts of the chip can also be altered by doping them with chemicals under heat and pressure. This process can be repeated hundreds of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each chip on the wafer is then tested for performance before it's separated from other chips on the wafer by a saw. Since microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an electrical charge. Resistors help control the electrical current. Transistors can either amplify or switch the electrical signals passing through. For more advanced chips, like those found on high-end graphics cards, there can be upwards of 28 billion transistors on board. More transistors on microchips allow them to send out more instructions, increasing the computational power. Moore's law predicts that computer chip manufacturing would advance at a steady rate, allowing transistor counts to double every 2 years. Based on the sheer power of the technology we use on a day-to-day basis, this decades-old prediction seems to still be mostly true. Manufacturers have been shrinking down their transistor sizes to fit more onto chips. Each breakthrough in transistor size has allowed the production of more powerful chips for our phones, computers, and gaming consoles. In recent years, they've gotten each transistor down to as small as 8 × 10 to the power of -8 inches in diameter, allowing an amazing 50 billion transistors to be crammed onto a single chip. Manufacturing microchips is truly one of our most complex feats, and yet innovations are happening every day.
Okay, that is a second videos about the manufacturing of the microchips, and maybe we have a question: how the manufacturer can produce in every small thing like a microprocessor? How they can be deliver some architecture of microchips into the small transistor, have the size of 2 nanometer. And for the explain that, I have a videos. It is about how microprocessor is work. So this is
Now, microprocessors are manufactured on the surface of a thin wafer of silicon, and I have one of them here. I hope you can see this. Each of those little squares is a single microprocessor of the kind that we saw earlier. Now, to me, it seems incredible that something which is so tiny and so complex can be made at all. It sounds almost impossible. Well, to see how it's done, we're going to have a go at doing something else, which also sounds impossible. And for this, I'd like a volunteer. Should we have someone from this side? Yeah, I bet you. Would you like to come on down? Okay, let's just turn that. Let's come and stand here. That's good. What's your name?
Briley.
Briley. Okay. What's your initials? What are your initials?
BG.
BG. All right. I'm going to give you a big marker pen. There we go. And I have here some rice, just ordinary rice. I'm going to take a little grain of rice. And I'm wondering, do you think you could write your initials on the side of that grain of rice using that marker pen?
Probably not.
Probably not. No, I think probably not either. Okay. Tell you what, to make it a little bit easier, we're going to do something different. Just wait there a minute. What I have here is just a sheet of plastic. What I'd like you to do is to write your initials, nice big writing, nice big fat writing, across the middle of that plastic for me. Okay? Excellent. Okay, that's good. Do you want to just go over that one more time? Make it really nice and big and fat. That's it. Lots and lots of ink is really good for this. Excellent. Wonderful. Okay, that's brilliant. Okay, let's just pop the top back on there. Now, what we're going to do with this, if you'd like to come with me, come over here. If you'd like to stand just there, we're going to take this and I'm going to pop it in this frame like this, and I'm going to switch on this light box. So this is just a box with a bright light inside. So lots of light is coming out, it's passing through your initials and spreading out in all directions. And over here we have a lens, and the lens is collecting some of that light and focusing it down onto this grain of rice. And we also have a camera which is looking at that little grain of rice as well. And if we can now take the feed, if we can take the feed from that camera and bring it up on the screen, if I keep out of the way of the light, we should just, there we can see, there are your initials written on a grain of rice. Okay? Okay, I'd like to do one more thing. Hold out your hand like this and put it in front of your initials, in front of the light box, that's it. And then hold it flat like that in front of the light box, that's it. And now just move it gently about, and we can see an image of your hand. Okay. Okay, thank you very much indeed.
Okay. I think this course is enough. So in this last moment, I want to recap our meet and our course. So actually, the computer can be produced, can be produced about image, videos, text, and etc. But the computers have a definition about a calculate. What is calculate? How they can calculate everything? They just can calculate about 1 and 0 condition. This is like binary. From binary is developed. This is developed again about hexadecimal and about AISTI standard and etc. Until he can be produced about the text, about image, about videos, and etc. And we know about the brain of the computer. We can call it chips or microprocessor or GPU. It's a miracle technologies. How the 1,000 transistor can be fetched in the one single chip. This is a technology about the manufacturing transistor to develop program. And the last moment, I want to say thank you, but everyone in this class. I'm so happy, and this is a last meet. this is a last meet with me, and the next week, every people in the class will be joining with Mrs. colleague Solika, and they will be talk about some instruction about problem and algorithm design development. And in the last, I want to give you a task. This task is I want everyone to to help me to fill the questionnaire. Okay, I want to everyone in this room give me fill the questionnaire. So this is I have some evaluate of some my teaching. Okay, I will share screen. Okay, in the chat box or text box, you will look about my evaluation of my style teaching and how I speak English and everything, what I do in this class. So you can fill it now. You can fill the name, email, and WhatsApp number is optional. And this is have some question about are you agree the lecture? If you are enthusiastic, attractive, or you agree my communication is good or not, especially in English language, and you can look about am I has properly organized or prepared for everything in the course meeting, and you can rate me, can the rating of me, how I performs on this course, or very good, or fair, or poor. I want to every student in this classroom, to be honest, to give your opinion. I think we finished about this class, and I want to use bahasa. Can I? Bolehkah saya memakai bahasa?
Boleh, boleh.
Boleh ya. Jadi silakan teman-teman untuk mengisi formulir ya. Jadi saya Pak Dimas ada formulir, silakan diisi. Silakan diisi formulirnya. Saya tunggu selama 15 menit untuk pengisian formulir. Jadi diharapkan pengisiannya jujur ya. Kalau memang dirasa Pak Dimas masih banyak kurangnya, ya silakan diberi catatan gitu ya. Biar Pak Dimas bisa menjadi lebih baik ke depannya gitu. Oke, sembari sambil kita menunggu pengisian kuesioner, bolehkah saya minta sesuatu kepada teman-teman yang ada di sini? Pak Dimas ingin teman-teman menulis satu kata positif di dalam satu lembar kertas. Kemudian nanti kita akan dokumentasi bersama atau foto bersama menggunakan kertas tersebut. Kira-kira diperbolehkan? Bagaimana teman-teman?
Boleh.
Silakan. Silakan ditulis kata positif satu aja, satu kata ya. Nanti kita foto bersama biar saya ada kenang-kenangan dengan teman-teman yang ada di UITM ini ya. Teman-teman boleh share WhatsApp nomornya, nanti siapa tahu saya kontak-kontak, bisa teks cakap-cakap. Nanti saya kenalin juga dengan beberapa teman-teman mahasiswa yang ada di Universitas PGRI Madiun. Siapa tahu kita bisa join kolaborasi, mengerjakan sebuah project seperti itu. Oke, silakan semuanya ditulis ya teman-teman. Terus nanti teman-teman yang ada di sini silakan on cam. Terus kemudian kita foto bersama gitu ya. Oke teman-teman, ini yang sudah mengisi kuesioner 15 orang. Ya. Terima kasih buat ini kakak atau Kak Ikra Isbin Munizam, Kak Nur Sabrina, Kak Triana, Kak Muhammad Hasib, Kak Ahmad Adi, Kak Adi Amir, Kak Ahmad Afifi. Oke, sudah 17. Oke, kita tunggu sampai penuh gitu ya. Kemudian silakan teman-teman menulis kata di satu kertas kosong gitu ya, seperti saya seperti ini. Oke, terus nanti ada kata-kata, terus kemudian ada tanda tangannya teman-teman gitu ya. Nanti kita foto bersama. Boleh pakai tanda tangan, boleh pakai inisial seperti itu, it's okay. Nama pendek gitu ya. Nanti kita dokumentasi bersama, foto bareng gitu ya. Nanti akan Pak Dimas buatkan video kenang-kenangan kita selama 2 minggu. Nanti teman-teman boleh tilik di channel YouTube-nya Pak Dimas gitu ya. Jadi mungkin saya nanti akan minta salah satu nomor WhatsApp-nya ketua kelas gitu aja ya. Nanti untuk saya kasih tahu hasilnya gitu ya. Ini sudah ada beberapa, sudah dikasih nomor WhatsApp. Thank you buat teman-teman yang berkenan memberikan nomor ya. Oke, terima kasih. Oke, sudah 20 mahasiswa. Saya rasa sudah cukup. Oke, and now silakan teman-teman on cam, boleh izin untuk on cam, kemudian menampakkan wajah ganteng dan juga wajah cantiknya. Terus kemudian mari kita foto bersama menggunakan kertas seperti ini. Oke. Nah, oh halo Mas Adib. Mas Adib berdua itu ya? Berdua, oke, tuh. Sama Mas siapa, Mas Adib? Kak Adib dengan siapa?
Ya. Saya bersama apa? Kelas trek.
Oh ya. Oke. Thank you sudah on cam. Yang lain? Oke. Ini ada Kak Ahmad Amar. Halo. Oke, Kak Lukman, Kak Irfan Razik, ya kan? Ini kalian tinggal di kelas apa di kos-kosan atau di rumah? Keren. Oke, kita tunggu yang lain ya. Kak Ahmad Afifi, kita tunggu teman-teman yang lain. Mungkin teman-teman yang lain masih mencari ide untuk menulis kata-kata puitis indahnya. Silakan boleh menata rambut gitu ya, supaya keren untuk di foto atau di video. Nanti akan Pak Dimas jadikan cerita buat teman-teman mahasiswa yang ada di Indonesia. This is my first experience to teach you guys. Oke. Oke, untuk teman-teman yang lain, tak nampak wajahnya. Apakah ini ada lagi di kelas, ataukah lagi di jalan? Kalau boleh tahu kakak-kakak kalian ini siswa tingkat berapa? Tingkat berapakah? Semester berapa?
Satu.
Oh, semester 1 ya. Berarti baru-baru semua gitu ya. Oke, kita 5 menit lagi ya. Kita 5 menit lagi dokumentasi. Kita tunggu buat teman-teman yang belum nampak. 5 menit lagi. Setelah ini ada kelas kah, teman-teman? Tidak ada.
Pukul 2 nanti.
Ada. Oke. Oke, bisa kita ambil dokumentasi sekarang ya. Silakan untuk on cam semua. Kita ambil kata-kata motivasi hari ini. Kita dari negara yang berbeda, tetapi tetap satu jua, sama-sama manusia, sama-sama ingin menjadi orang besar ya, bukan orang gendut, tapi orang sukses. Oke, oke, silakan, silakan teman-teman menunjukkan hasilnya. Nanti untuk saya screen gitu ya. Oke, tunggu apa-apa, saya mau mengambil foto dulu. Silakan, semuanya dihidupkan. Oke, itu ada yang kebalik itu. Muhammad Daniel, itu tulisanmu kebalik. Ahmad Daniel itu kebalik itu kelihatannya. Kamu pakai fitur kamera di mirror ya? Oke. Oke, ada lagi yang sudah? Oke, sebentar. Saya coba screenshot. Siap, aba-aba ya. Saya hitung. 1, 2, 3. Oke. Lagi, sebentar. 1, 2, 3. 1 kali lagi sebagai penutupan. Tahan. Oke, kasih senyum yang terbaik. Giginya dikelihatin. Oke. Oke, sebentar. 1, 2, 3. Oke, terima kasih teman-teman sudah berpartisipasi dengan kelasnya Kak Dimas. Semoga ilmunya bermanfaat ya. Kalau ada waktu mungkin teman-teman bisa buat WA group, nanti bisa ngobrol-ngobrol sama saya gitu ya. Oke, saya rasa sudah cukup untuk pertemuan kali ini. Terima kasih. Thank you for everything, for everyone. I hope you can enjoy the moment with me. And if you want atau misalnya teman-teman pengen punya grup WA, kita ngobrol-ngobrol pakai bahasa santai, it's okay, nggak masalah. Mungkin kita bisa tukar budaya seperti itu. Oke, kurang lebihnya Pak Dimas, mohon maaf. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Terima
Salam.
kasih Mas Dimas.
Terima kasih, Pak.
Terima kasih, Pak. Terima kasih, Pak.
Makasih, Pak. Makasih, Pak.
Terima kasih Pak.
Thank you,
Terima kasih
sir.
Pak.
Sama-sama. Main-main ke Indonesia. Kalau sudah jadi orang sukses ya.
Makasih, Pak.
Ya.
Thank you, sir.
Bye-bye. Bye-bye.
Bye.
Bye-bye, Pak.
Ya.